Welcome back to Multivariate Calculus. In this video, we're going to be talking about arc length. The idea of arc length is something that we have talked about previously in the calculus of a single variable. If I look at a curve in space, I can ask the question of how much distance do I travel if I follow along that curve? That question is the question that is arc length. And so the difference that we're going to be looking at now, the change in what we're doing now compared to what you've seen previously, is that I want to assume that this curve is somewhere in three-dimensional space. And instead of giving the equation of the curve as a function, I'm going to give it as a parametric system or a vector valued function. All right, so let me get my head out of the way and let's take a look at what's happening here. So for a vector valued function or a parametric equation, remember that the idea is that we have an origin somewhere in space. And the vectors will point to various places along the curve. And it is important that when we talk about the graph here, right? So if we're looking, it looks like we're just highlighting this portion of the curve. We're talking about the coordinates for the curve on the interval from t0 to t3. One other thing that we have to be at least a little bit concerned with in this process is that unlike when we had a Cartesian function in calculus of a single variable, there is nothing in a parametric system that prevents the motion from doubling back and forth over and over and over again. So we do need to make sure that that's something that doesn't happen. And to do that is actually fairly straightforward. In order for the motion of a particle to slow down and come to a stop, and then turn around and go the other way, the only way for that stop to occur is if the velocity is zero. And in kinematics, we know that the velocity of a particle is the derivative of its position. So we have the position function pointing to this location. Its derivative is the velocity. In order for a particle to turn around, it has to come to a stop first, which means that the derivative would be zero. So we are going to simply insist that r prime of t is never zero on that interval. The derivative never zero. That feels familiar to us. That was the thing that we talked about when we first started graphing functions as the definition of a smooth curve. So we need the curve to be smooth in order to talk about the arc length. And as long as that's the case, then we will have nothing to worry about. Now, as we talked about in the previous video, the derivative of the function, in addition to needing it to be non-zero so that things work out nicely here, the derivative is constantly giving us the equation of a tangent vector. So if we calculate the length of that tangent vector, or length along that tangent vector in a bunch of different pieces, that will give us a nice approximation. So the arc length, let's try that in blue, which is actually visible. The arc length is the sum of the lengths of all of the tangent vectors. But in order to, doing here, arc length, we use S. I started erasing things and I got myself mixed up. But in order to go from an approximation of a bunch of straight lines to the exact length of the smooth curve, we take our time step, our little pieces that go from one vector to the next one, and we compress that down to t goes to 0. And taking a summation as the pieces that we're summing go together to be infinitesimally small, hey, that's what the integral is all about. And so we have an arc length formula for dealing with vector valued functions. This can be easier to deal with than the arc length formula for Cartesian functions. It can be more challenging, just depends on the situation at hand. Let's go ahead and just dive right in. Let's go ahead and set r of t as the cosine of 3t I hat minus 4t j hat minus the sine of 3t k hat. We also need the interval on which we want to consider this function. So maybe something like for t in the interval from 0 to, say, 3 pi over 2. That seems like a nice place to go. And if we're going to be looking at this curve and trying to figure it out, then we should go ahead and graph it first. So let me jump over to GeoGebra. Actually, let me first close that interval, then jump over to GeoGebra, where we have this thing graphed. And if I stretch this out so that you can look at the definition of the curve, you will notice that I specifically set that t goes from 0 to 3/2 pi. So I have my interval set up correctly, and that is important. And we can move this around and we can look at, all right, we've got a kind of normal looking cosine in the XY plane. We've got a mostly normal looking sine in the YZ plane. And if we come over to the XZ plane, it looks like an oval, but if you pay attention to the scaling, it's not a linear scale, and this actually is a perfect circle. And I think that this view is the most telling of what's happening. What we are looking at in this curve is, if I can do this very nicely, we're starting here. We're taking a full loop around, a second full loop around, and then about, and actually if I tilt that down, exactly a quarter of the third loop. So you can see that it stops exactly at the top, 1/4 of the way around on its third loop. And so that gives us a picture of what we're looking at. We can look at the function, we can determine that while each of these things can be 0 within that interval, they're not all going to be 0, so nothing weird is going to happen with the graph. And we can go ahead and continue on with our analysis. The formula for the arc length tells us that we want, first of all, the derivative, r prime. Derivative of cosine of 3t will be -3 times the sine of 3t in the I direction. The derivative of 4t is 4. The derivative of sine of 3t is 3 times the cosine of 3t. I forgot my j hat. K hat is also necessary. And that's great and all, but what we really want is to find the magnitude of this curve. And so we want to take the square root, and each term on its own we will square. So we've got -3 sine of 3t squared, we've got -4 squared, and we've got -3 cosine of 3t squared. All right, -3 squared is +9, sine squared is sine squared. -4 squared is +16. And -3 cosine 3t squared is +9 times cosine squared of 3t. And what do you know? We chose some functions very carefully, so we have a sine squared and cosine squared. If sine squared plus cosine squared is equal to 1, then 9 sine squared plus 9 cosine squared must be equal to 9. Then we have 9 plus 16, which is 25, and the square root of 25 is 5. A lot of care went into making this actually comprehensible. That doesn't normally happen, but we got lucky this time. And so finally, we want our arc length, which is the integral from our starting point, which is t, to our ending point. Our starting point t equals 0 to our ending point, t is 3 pi over 2 times the magnitude of that derivative, which we just calculated is 5. And then, again, this problem has been very carefully chosen so that the integration itself is easy. Before I go on and finish this problem, I want to reiterate something I said near the beginning of the course. The actual performance of the calculus, the differentiation and the integration, I generally try to make that part fairly straightforward so that you don't have to spend hours bashing your head against the wall. You learned how to perform all of these integrals and all of these derivatives, and it certainly is something that could happen. But the interesting question in the problems that we're looking at is generally, how do you set up the integral? How do you work around the integral? And actually performing the integral is kind of boring, so we try to avoid it whenever we can. Not to say that you'll never see it, but that's not going to be the common thing. Right? The integral of 5 dt is 5t. Right? 5 times 3 pi over 2 is 15 pi over 2. 5 times 0 is 0. So the length of this curve is simply 15 pi over 2. All right. To extend this idea of arc length a little bit, let's go back and think about what arc length really means, or what a parametric curve really means. The parametric curve is tracing the path that the vectors point to as they evolve in time. So if I jump over to GeoGebra, you can see I have a couple of other things set up on my graph now, and I've zoomed out quite a ways. But I have my point here where my vector valued function is going, and I've set it up so that it traces out the path as this evolves in time. And thinking about the path in that way introduces a new question we may want to ask ourselves. Instead of setting a path and setting a particular length and saying, how long is that? We might want to instead say, well, can we set this up as a function? Can we set it up so that we know, based on how we control the movement of this object in question, where is the path, or how long has the path been this far into the process? So instead of just arc length, if I hit the right button, we can write the arc length function. The arc length function is written as s of t, and it's going to be defined as the integral from 0 to t of the magnitude of r prime of tau d tau. All right, a couple of weird things going on here. First of all, again, this equation is telling us what is the arc length of the path this far along in time. So starting at t equals 0 and going until the current time t, how far have we gotten? Then we have the Greek letter tau that shows up here in these two places. And this is a dummy variable or a placeholder variable. In the regular arc length formula, we just used the letter t there and it was perfectly fine. But now t has another meaning right here. It's the limit of integration. And having t in here and also having t out there can be really messy and confusing, and it can make people make mistakes, and we don't want to make mistakes. So for that reason, we change the variable inside the argument to be something else. It's a placeholder variable. Tau is fairly popular because it kind of looks like the letter T, but a little bit different. I've also seen people use A or theta or random squiggle, right? Variables don't have any inherent meaning on their own. It's the meaning that we give them. Any symbol that you can faithfully reproduce can be used as a variable. It's just that letters of the English alphabet and letters of the Greek alphabet are the things that are the easiest for us to communicate, so those are the ones we use. All right, so going back to the same curve that we had just been looking at, we had r of t in component form. It was cosine of 3t, negative 4t, negative sine of 3t. We had it in unit vector form before, but we can write it in component form, and we know it means the same thing. And we still know that the magnitude of r prime of t is 5, right? We've already done that calculation. We don't have to do it again. And so s of t is going to be the integral from 0 to t of the magnitude of the derivative of the vector valued function, which is 5 d. Again, we don't want to use t there because we already have t, so we use some other placeholder like tau. And so we get 5 tau evaluated at 0 and at t, which is going to be 5t minus 5 times 0, which in this case is 0, so we don't bother writing it down. And we can now talk about the arc length parameterized and how far is the arc length going to go each step along the way. So that's the basic idea. Let's look at one more for you to take a chance to play around with. All right. Giving it in component form, let's find the arc length function for the parametric curve. R of t has components 5t, 3 times the sine of 4t, 3 times the cosine of 4t. All right. So take a couple of minutes, see what you can come up with that problem, and I'll see you in the next video.